Hello everybody, yes, my name's Patrick. Today I'll be running through a 3D model of a semi-detached house alongside the MasterSeries Masonry Wall Design Module for the purpose of providing you with some common examples of where and how the Masonry Design Module can be used to design wall panels in a domestic setting. So I hope this example covers a lot of the different scenarios of wall panel designs that are applicable to also many other types of masonry buildings or structure types. The purpose of this webinar is to give you some insight into how the software can assist you in designing wall panels more efficiently. This is aimed at both users and non-users, as it will outline some of the capabilities of the software which should be useful for both. And even I have learned a few things in researching the module deep myself. So again, I'll be using a third-party software tool, SketchUp, for demonstration purposes. And as usual, none of this should be taken as design advice. All designs are independent, and it is extremely rare that any two design scenarios are exactly the same. So you, as the engineer, should know what you're doing and what the software is doing. So I would also like to mention a quick thanks to Aimson, Structural and Civil Engineering Design, who were able to impart some of their knowledge and experience of the use of masonry in a domestic setting for the benefit of the webinar today. So just to start, I'm going to go into the background of the yield line analysis, not too much. We did cover it in a webinar last year in a bit more depth, and we've got some useful technical notes on it. But the MasterSeries Masonry module, it's unique versus competing masonry design software packages in that it utilises advanced yield line analysis to check wall panels laterally for out-of-plane loads, which in many cases is the critical design check for a panel. The yield line analysis method gives a much more accurate and generally less conservative design for laterally loaded masonry panels than the more traditional standard panel methods taken from both Eurocodes and the British Standards. So today I will almost exclusively be referring to the yield line analysis capabilities of the full version of the Masonry Design Module over the more traditional method, which is also an option in the software. So I'll start off, I'm going to bounce between a few PDFs here. We've covered in depth in this MasterSeries technical note titled the Masonry Advanced Yield Line Analysis Method. It states that the codes, for example, the British Standards and Eurocodes, provide tabulated values of bending moment coefficients which relate the wall length, height, and orthogonal ratio of the flexural strength of the masonry for both the parallel and perpendicular directions. However, in both British Standards and Eurocodes, the use of a recognised method of obtaining bending moments in flat plate, for example, yield line or finite element, is permitted, and as such, the yield line method is permissible under both the British Standards and Eurocodes. And in fact, I'm going to open up a Brick Development Association publication here. This is a good short publication summarising it, and as I said earlier, these are the type of tabulated values that the traditional method is deriving the values from. And it states in here to start what I mentioned there. Alternatively, a yield line analysis from first principles may be used, and it refers to this guidance in practical yield line design, which I can also pull up as well. This is a publication which, if you want to go into more depth, you can read through here. I think there's a good summary at the start there, frequently asked questions as well. So what the yield line method is, it's a plastic analysis method which establishes the load at failure based on the assumed failure mechanism and yield line pattern. So the yield line theory determines how the wall should feel, and then works back to tell us how far away we are from that failure based on the parameters we have input, and that usually is represented in the software as a utilization ratio, which we can show later. So the yield line theory was originally developed to analyse reinforced concrete slabs, and was initially thought that the masonry was too brittle to apply the method to, but over time that they have found that the compatibility between the failures predicted by testing and the failures predicted by theory are correlate. So if we go down to page 20 there, we get a little excerpt from that publication there. So back to our SketchUp model. So starting by looking at a standard semi-detached building here with some very typical common wall panel types and how they can be dealt with. Most, if not all of you, may be familiar with this type of house. This varies a little bit from the standard semi-detached layout in that it has an extended rear, which will allow us to demonstrate some additional features of the software, as you'll see. We'll be referring to the software throughout the different wall panel designs, and the layout of this house is indicative, but a bit of a caveat here. So I made it up myself in the space of a few days, and I'm aware that it's not complete, but its primary purpose is to show you the different wall panel types. So if you see any bits of house floating in midair, or any rooms without any doors, or try not to pay attention to those minor details. So going to the front wall, we don't have the option to model a full panel here with internal fixities, so we should split the wall panel up within MasterSeries. So here we're looking at 4 different wall panel types here, which are each fairly straightforward. So we will assume throughout the property that the walls are standard cavity wall, 100mm thick brickwork outer leaf, 100mm thick blockwork inner leaf, and 100mm cavity with wall ties, etc. So as mentioned earlier, we can go through this with the masonry wall designer alongside. So looking at wall panel 1 here first, taking the fixity conditions. On the left hand side, we have a perpendicular party wall, which we can take as continuous, therefore assume a fixed support here. Similarly, on the right hand side, the internal return wall will allow for continuity on our cavity wall, and along the bottom, the floor joists on the first floor will provide continuity, therefore again a fixed edge. And the roof will be supported on the inner leaf by the roof truss, and we can assume top support condition as pinned. And for our loads vertically, we are providing support to the roof from the inner leaf, and therefore we will apply the roof dead and live loads, taking into account the eccentricity of the loads. And laterally, the wall panel will be subject to wind load. So if I bring up my MasterSeries model, so we can see wall panel 1, front wall top left. You can see the fixity conditions there we've modelled match what I just showed in the sketch up there, and we can also apply our roof loads there as well, and we get an easy pass with a utilisation ratio of 0.51. We can switch actually off the Evanci line analysis and see similar results, so it's not a very advanced panel, so that passes. Wall panel 2 on the bottom left, again, along the top there, the floor joists on the first floor allow for continuity, therefore again a fixed edge. The left hand side, a continuous fixed support due to the perpendicular party wall and continuation onto the neighbouring property. The right hand side of the panel, again, the internal return wall will allow for continuity, again, therefore fixed. And the bottom, damp proof membrane, which will impact the moment resistance of the wall, so we will assume a pin support here. I'll note the moment resistance can be enhanced by vertical load and properties of the DPC material. So I'll pull open the British Standards here as well. There is a few lines in there about that. Referring to clause 20.1 of the British Standards for flexure. Flexure tension should be relied on at a damp proof course only if the damp proof course consists of material that has been proven by tests to permit the joint to transmit tension. So that'll be on you as the engineer to verify that. As I say, in this case, we'll assume it as pinned. Loading vertically, we will manually take the loads from the panel 1 above and roof loads and apply as a UDL on the current wall. The floor joist at level 1, we will apply that as an eccentric load on the inner leaf. And laterally, again, the wall panel will be subject to wind loads as the panel above. So again, I'll pull up on my MasterSeries and go to the next panel, and we can see our eccentric vertical loads and then the self-weight of the panel above and our out of plane lateral loads there as well as our opening. So we also get a pass on that. Wall panel 3 in the top right. Restraint wise, we're looking almost at a replication of wall panel 1 for both fixity and loading, albeit with slightly less roof loading due to having our hip end there. And wall panel 4 on the bottom right, again, similar to panel 2 on the left, but we'll have the same restraint conditions and loads to consider on the panel, but now we have to consider 2 openings here in the form of a window and a door opening. Again, we'll be taking the vertical loading from the panel above directly down. So using the E-line analysis, checking panel 4, we have a pass, but it's a good example of when, if we turn that off, we get a failure by using the traditional panel method. If you did want to reinforce that, you could specify some method of reinforcement via a return wall or a wind post or even local thickening of the wall. But if you're using an advanced E-line analysis, you can justify that wall panel there. So next, that was a front wall. Now we'll go on to the side wall. We will strip away that and start with wall panel 5. So as you can see here, we get no restraint in the middle of this panel due to the presence of the stairs. As there's no openings in this panel, actually, it'll give us a good chance to compare this full length wall panel in both the advanced yield line analysis and traditional method and see how similar their outputs are. So if we go to wall panel 5, looking at the summary output between both advanced yield line analysis and the traditional methods, we can see that there's very little difference when we switch between the two. As I mentioned earlier, that is because the panel method derives from the yield line methodology, and probably the slight difference there in the moment capacity output is due to some interpolation between the tabular values or maybe some rounding up or down of the outputs within the traditional method. So we can go on then to the next wall panel 7, and by inspection we can probably guess that it's similar to wall panels 1 and 3 from the front wall, which we're well on, except this panel is slightly smaller, so proportionally the opening will be larger. I think that's a pass as well. Yep. I should mention that the joists in this case, they're not running directly into the wall panel, so the engineer will have to detail this such that the wall abuts the floor joists and the wall can get restraint from the floor joists. This detail is not shown here, but for example, you may expect to see some noggins on the floor joists in reality, and some strapping to the inner leaf of the external wall. Wall panel 8 now, something similar again. Next, so just slightly bigger. I've got my load takedowns shown there. So slightly less roof loading on that wall panel than the others. So slightly less compression in the wall, which generally assists with increasing the flexural capacity, but doesn't really make a difference here. Wall panel 9 is where it gets interesting. So we can see a beam taking this wall panel above and spanning on to the external wall. So it's significantly longer and has a point load between our two openings supporting the wall panel above. I'll maybe turn that on just so we can see the openings there. Again, our restraint conditions are similar. We are fixed at either side and at the top, and pinned at the base at the location of our DPM. And loading, we've got no vertical loading directly from the floor above because the wall is spanning in the other direction, but we will have the self weight of the brick and blockwork on both leaves from the panel above, and we'll have some roof load coming down as well, making its way down through the inner leaf. We'll have to apply those. Also, we will have lateral loading, again, taken at 0.75 kilonewtons per metre square, and then we also have a point load to apply onto the panel. And we can specify what area this load gets distributed over, whether the beam sits directly on the wall itself, or we can specify a pad stone to ensure we don't exceed the bearing stress capacity of the wall. So I want to note that any point loads that we do put in the wall is distributed on the wall panel itself and not into any vertical wind posts or piers that may be located at the same position. So if I open up our wall panel 9, we can review our loads here. We've got our inner leaf wall loads, we've got our outer leaf loads from brickwork panel above, and then we've got our lateral loads. Then we've also got our point loads there. We can then review the pad stone as well. So we can look into the detail for specifying bearing lengths and potential pad stones as well. So the software carries out a local stress capacity check based on the input we give it. We get a pass on this wall panel, but I'm going to play about a bit here and just to show you some of the different features of the software. So the first thing I'm going to do is increase the wind load on this wall panel so we can just get a failure. We have 3 different options here for reinforcing the wall locally. The first thing we can do is put in a wind post here. As I mentioned, the wind post, it won't actually transfer any vertical load to the base in the software. All vertical load from the coincidental point load will go directly into the wall panel, and you'll need to ensure it is detailed as such. I have a wee pad stone shown there just to show you that's what the beam is sitting on and not directly the wind post. The wind post is treated as bending only or non-axial, so it's not the equivalent of a vertical supported edge, as it has a limit to how much flexural capacity it can take, and the post is treated as a simply supported either end by default. You can also specify the post to break the continuity of the wall panel on each leaf, and the one post does not act compositely with the wall panel, although it does act in unison. So if I go back into the software now and I specify a one post at 3 meters along there, and I'm going to give it something with a low moment capacity, like I'll go and put on a small equal angle, like a 50 by 50 by 5, because I want to just see it. I want to see it just passing. So you can see there, it's just passing. And a common misconception is that the one post will act similar to vertical support, and this is not the case. It's only contributing to the stiffness of the wall panel locally. And we can see the yield lines actually passing through here. The one post is acting in unison with the wall, adding to its flexural capacity, but it's not acting the same as a vertical support. You can see the yield line actually passing through the location of the angle. If we increase that one post then to a 100 by 100, say, we can see the yield line changes then, so it only affects one size of the wall panel. It's also worth noting that the yield lines showing represent the failure lines of the panel that fails first. For example, if we increase this value to 3 kilonewtons per meter squared, we get a much bigger failure there. MasterSeries still calculates and checks all the possible yield line patterns in the background, but it only shows the most dominant failure lines. So we can see the right hand side of this panel failing at around 46% over, but this does not mean that the left hand panel doesn't fail. It only really means that the right hand panel fails before the left hand side does. So that's worth knowing if you ever come across that and you think that one side of the wall panel passes and the other side fails. That's not the case. It's just highlighting the panel fails first. So I'm going to change those loads back to 1.25, and we're going to take out this one post and replace it with a pier. Go back in here and talk a little bit about the introduction of a pier. So a pier acts in bending to stiffen the wall panel. Again, it's not the same as a supported edge. Again, it does not transfer vertical load, and nor does it act like a buttress, so it doesn't transfer loads back into the ground. It behaves like a T-section, so this behaves compositely with the wall panel as it is from the same material itself. So if I go in and I manually remove that, so I'm going to delete my one post, and then I'm going to add the stiffener. So I'm going to say that it's a stiffened wall, and then we're going to specify the distance to the center of the pier, and then we're going to say that's 3 meters, which is the same location as our point load coming down there. Pier centers, say 5 meters, just to take the next pier outside of the boundaries of the wall, and then the pier thickness, we're going to say let's pick something small. That's 300 mil, for example. I want to show the same as I showed with the one post. So it's a 300 deep and 100 thick. So again, we're getting a pass here, but we can see the yield line passing through the location of the stiffener. If we increase that to 1000 to increase the flexural capacity of the pier, we can see it a lot stiffer now, and the failure is isolated to the right hand side of the panel. So it's important to understand that a pier is not the same as a vertical support, nor is a one post. So it does not behave like a buttress, which transfers the load back into the foundation. It only stiffens the panel locally based on the support conditions of the panel it's connected to. So hopefully that makes sense. If there's any questions on that, just fire it into the chat. Go on to the rear wall. Finally, we can look at the rear wall panel with openings here. It's got a window opening on the top floor and a double door opening on the bottom floor. This end wall panel will need to transfer the wind loads being applied on the side of the property down to the foundation, and the wall will be required to resist both moment and shear, as well as our vertical and lateral loads, considering an increased lever arm for resisting the moments generated from the loads at first floor. In many cases here, we would have a goalpost frame specified. Building regulations specify rules for buttressing walls, and it's common to specify steel frames in this condition, but with some additional checks, you may be able to get away with just the buttressing alone. So if we look at wall panel 10 here, our restraint conditions will be both fixed both at the side and at the bottom and pinned at the top. Vertical loads again will come from the roof, and lateral loads again will be applied, and we will have to work out the total load from the wind on the side walls onto this wall panel. So if we open that up in MasterSeries and we go to wall panel 10, I'll open up the in-plane loads. You can see how they're applied. So our racking shear force is applied as a total load in kilonewtons on the side of the wall and not as a kilonewton per meter run. And our in-plane moments can be applied by taking the shear force for this wall panel, and the lever arm will be taken at the mid-height of the wall. These really should include the shear force and the moments from the wind panel on the roof as well. And we can also tell the software to share the loads between inner and outer leaf at 50% each. And in this case, we get a pass again. So we can now look at our wall panel 11 below. So this will be a more critical design check. It'll be resisting the additional shear force and moment from the floor above, considering that longer lever arm, which will increase your moment forces. So again, if we go to wall panel 11, if we look at our in-plane loads, again, these will be manually input into the software. And in this case, using a standard cavity wall, we will get a failure. So if we look at the failure, it is due to localized tension stress, and that is happening. If we look at our load takedown diagram, we can turn that on up here and check both inner and outer, and we can see localized tension stress here. So we can see the distribution of stresses on the wall for the worst load case. And if we want to make the wall pass, we can go into our wall setup and change the thickness of the inner leaf to 215. And then it's good practice then to tell the, let me see, in-plane loads, share the outer leaf contribution relative to the thickness. So 215, let's say it's about 33%. So the outer leaf contribution will be taking 33%. So we're getting a warning there. Also, I'm going to show you the effects of the MZ distribution here. So if we turn that on, we can see how this affects the behavior of lateral loads between the left hand and the right hand side panels. And in this case, we should be keeping it turned off, as we're assuming this narrow top slither of masonry just to be transferring the horizontal loads between the two panels and not any moment. So the wall panel is not acting as one. It's acting as two different wall panels with just this top wall panel transferring the loads between the two. If you just had a small opening, for example, you might want to keep that on so that the wall panel is acting as one. So this side's in tension, this side's in compression, but we want to make sure that the moment's shared between both. So let's say with this failure, we could maybe go ahead and specify a steel frame, but potentially some engineering judgment can come into play here, as we can assume that the load will redistribute here to the compression zone in the ultimate state. So we're also ignoring the effect of the return on the wall. So it's a very small local tension stress, and we're not assuming any cracking here. If you were to assume some cracking and some redistribution of the moment there in the compression zone, you might assume a pass on this. Anyway, that's just an overview of some wall panels. I'd planned to maybe show a few additional wall panel types, but I think with that there example, we can cover most of our bases there. Ultimately, it's up to you as an engineer to make the call on any of these decisions within the software, but as long as you understand the different applications of the different features within the software and how they're applied. Andras, I'm going to switch back to you.
So ladies and gentlemen, if you have any further questions, you can get in touch with us on our usual channels. And if you want to try out the software, just go to the MasterSeries website, masterseries.com, and fill in the request to do so. So ladies and gentlemen, again, thank you very much for attending and have a great day.